Good afternoon, everybody. Today we're looking at two rational functions, f of x and g of x, and we're going to look at a composite function of the two, f of g of x, and we're going to sketch it and write its domain and range. Okay, it's going to be a rough sketch, but that'll be enough for today. Okay. So first of all, in finding that composite function, f of g of x, what that means is everywhere that we see an x in f of x, for us that'll just be this one, we're going to replace that x with all of g of x. So everywhere we see an x in f of x, which means just here, we're going to replace x with the entirety of the function g of x. Okay, so let's go ahead and do that first. The composite function f of g of x is going to read 1 over 1 plus, and we replace x with g of x, so 1 over 1 plus 1 over 2 plus x. Okay, now obviously we can simplify this a little bit. So let's first get a common denominator for our denominator. And so 1 is the same as 2 plus x over 2 plus x. And so now we've established a common denominator, so we can combine the numerators, right? So this means we'll have 1 over, we can combine the numerators, 2x plus 1 is 3 plus x. So we have 3 plus x over 2 plus x. And now we have 1 over a fraction, so we can flip and multiply. And if we flip and multiply, we're flipping and multiplying by 1. And so we're going to end up with x plus 3 over x plus 2. Okay, now this you might be aware of is a transformation off of the function 1 over x. Now you could do an analysis of a rational function where we have a linear factor over a linear factor. We can get the root, the vertical asymptote, and you're free to do that if you want. Or the way that I have my students deal with it is to put this into transformational form. And so we're going to force that denominator of x plus 2 in the numerator and then balance it out. And so x plus 3, that's the same thing as x plus 2 minus 2 plus 3, right? I just added 2 and subtracted 2, which means adding 0. But now this is the same as the denominator, right? Because this is all over x plus 2, which means that now I can separate this into two different terms. I'll have x plus 2 over x plus 2 minus 2 plus 3, that's plus 1 over x plus 2, right? And then let's clean that up. And so x plus 2 over x plus 2, that's just 1. And so to put it into transformational form that you're familiar with, I'll have 1 over x plus 2 plus, right? This term is equal to 1, and so plus 1. Now, this you might recognize as a transformational form off of the parent function 1 over x, right? All we have here is there's no vertical stretch. We'll have a vertical translation of positive 1 and a horizontal translation of negative 2, right? So putting that on our sketch means we're going to have a vertical asymptote at x is equal to negative 2. So we can pop that onto our sketch, labeling it as such. And we're going to have a horizontal asymptote along the line y is equal to 1. That's 1, something like that, right? Again, labeling it. Connecting it to an earlier concept of rational functions. Remember, if your rational function has the same degree in the numerator as well as in the denominator, we have a horizontal asymptote, that is the line defined by the equation y is equal to the ratio of the leading coefficients. And for here, that would be 1 over 1, right? The leading coefficients are the x coefficients, and 1 over 1, as you know, is 1. And so hopefully that confirms something you already knew, right? A concept of rational functions, more generally speaking. And so now we have our horizontal and vertical asymptotes onto our sketch. There's no vertical stretch, and so we can use the classic pattern that we have for 1 over x transformations from the center of the cross of the asymptotes, right? We can go over 1, up 1. And so this is at negative 2 and positive 1. So this will take us to negative 1 and positive 2. Negative 1, 2. And likewise, we can go back 1, down 1. So that means negative 3 and 0. Negative 3 and 0. And from there, we can roughly sketch our boomerangs the way that I encourage my students to do so, right? Hovering along the asymptotes, horizontal as well as vertical, and likewise in the bottom left quadrant. This should confirm we have a root at -3, right, from our numerator of x plus 3. This should give you a notice that we have an x-intercept when x is -3, so that's confirmed. And here we have a y-intercept here that looks like it's between 1 and 2, let's say. And let's see what happens when we plug in an x value of 0. We get 0 plus 3 over 0 plus, that's 3 over 2, that's 1.5. And so this looks appropriate at 0, 1.5 for our y-intercept. And so this is our resulting f of g of x function, right? That's what this sketch is of. And so to finish off our problem, what is the domain of this f of g of x composite function? Well, f of g of x is going to have a domain of xer, except at the vertical asymptote, meaning that x can't be equal to -2, but otherwise x can be any rational value. And the range of this composite function, the range of f of g of x, is all y values other than the horizontal asymptote along the line y is equal to 1, because we never cross it. And so again, y is never equal to -1. But other than that, y can be any real value. And that concludes our problem. And so again, any composite function means we plug in the innermost function into the outer function, right? Plug in the inner g of x into the outer f of x. Replace every x in f of x by the entirety of g of x. And that's how we deal with those. So I hope this helps, and thank you for watching.